Good morning again. Today's lab experiment is Ohm's law, linear and nonlinear devices. So a linear device is when the resistance remains constant as you put more current through it. And as a result, when you plot voltage versus current on a graph, you get a straight line slope that you get a straight line with a slope that equals the resistance of the resistor. So that's a linear device, but we're also going to look at a couple of nonlinear devices as well today. So before we get into the meat of the experiment, we're going to introduce a couple of concepts. The first is called current. And current is a measure of the amount of charge passing a given point in a circuit per unit time. And so if you know the charge or the total charge that passes through as a function of time, you take the derivative of that, and that gives you the current. And current happens when there is a potential difference between one side of the circuit and the other side of the circuit, or between one end of a segment of the current and the other end of the segment of the current. So if there's a voltage across, or there's a potential difference between two ends of the circuit, a current will flow. So the direction of current flow is defined as going from positive to negative, even though it's the negatively charged electrons that actually do the movement. But Ohm's law says that if there's a potential difference across a segment of a circuit, that that potential difference is equal to the product of the current going through that segment of the circuit multiplied by the resistance in that segment of the circuit. So for an ohmic or a linear device like a resistor, the resistance remains constant, and again, a plot of voltage versus current gives a straight line with a slope equal to R. But we're going to look at some nonlinear devices as well, and so that the resistance can change with the amount of current that's going through. So we're going to look at a regular resistor, and we are going to look at two nonlinear devices. So for the first part of the procedure, and each part of the procedure has its own video clip associated with it. So the first part, we're going to take a 1,000 ohm resistor with a nominal value, or a nominal value of 1,000 ohms. And we're going to look at the color code, because resistors have a universal color code. And so the first two bars in the color code represent 2 digits of value. The third represents the multiplier, so times 10 to the watt. And then the fourth bar, if there is one, tells you the percentage uncertainty in that resistor. So you could have two identical looking resistors that don't have exactly the same resistance. But we're going to look at the color code, and we're going to use the digital multimeter to measure that resistance exactly. So in part 2 of the experiment, we're going to take 2 digital multimeters, one to measure current through the circuit, that you connect ammeters in series with the circuit, and the other is going to measure voltage. And so you're going to use that to measure the voltage across the circuit, or rather the voltage across the resistor, excuse me. So you're going to get 10 measurements between 0 and 15 volts. So we're going to have a circuit connected to a power supply, and we're going to vary the voltage between 0 and 15 volts and get the corresponding values of the current that go with it. And I forgot to reverse the resistor. So that was a part that's not included on your video, but you do go up to 15 volts. You're going to plot delta V versus I, include error bars. So what's your uncertainty in your current measurements? What's your uncertainty in your voltage measurements? And include those. You can do that using Excel. Get the slope, and calculate the slope and calculate the uncertainty of the slope, which is also something you can do in Excel. And so I have those instructions posted on Blackboard. And so you'll see if your slope agrees with the measured value of the resistance within your uncertainties. For part 3, we're going to be using the first of our nonlinear devices. This is a light bulb that uses a tungsten filament, and as the current increases, the temperature in the filament increases and the resistance increases. So you'll notice you calculate the resistance of the filament at room temperature, before you put it into the circuit. Then you're going to connect it where the resistor was. And you're going to get 10 measurements between 0 and 7 volts with corresponding values of current. So you're going to use Ohm's law to figure out the resistance as the current goes up. And then you're going to calculate the temperature. Again, given it's a tungsten filament, so you can figure out its temperature coefficient of resistivity. And with that, you can figure out the temperature as well. And so that's another column I want you to put on that table. For part 4, and this is the last part, you're going to connect what's called a diode in series with a resistor. Now, a diode is also a nonlinear device. It adheres to some quantum mechanical principles, so it's not necessarily as easy to explain why things happen the way they do in a diode. But the primary function of a diode is to permit current one way and to block current the other way. And you'll be able to see that very clearly in the video. So you're going to get, and so I had a third multimeter, which made this simple. So I connected I measured the voltage across the power supply and used the third multimeter to measure voltage across the diode. So you're getting the voltage across the power supply, the voltage across the diode, and the current. So we had 3 multimeters going for this experiment. So repeat the, go 10 times between 0 volts and 10 volts, and you then reverse the diode, basically disconnect the diode, flip it around, and reconnect it. And so you're plotting delta V versus I both ways, and calculating R for each entry both ways, just like you're doing that in part 3 as well. So we want to talk a little bit about the uncertainties in your error analysis. So you're calculating the resistance is the voltage divided by the current. So the uncertainty in your resistance is equal to your calculated value of the resistance multiplied by the square root of the ratio of your uncertainty in your voltage to your voltage squared, plus the uncertainty in your current divided by the current, also squared. And so you're squaring those fractional uncertainties, adding them together, taking the square root, and then multiplying by the resistance. In the formula that you're using to calculate the temperature, you're using the formula for the temperature of resistivity. So you have the resistance is equal to the initial resistance at the reference temperature. So your reference temperature is the room temperature, which I have. That's in Fahrenheit. You're going to have to convert that to Celsius so that you get your final resistance in Celsius. So you have your initial resistance multiplied by 1 plus alpha. This is the temperature coefficient of resistivity. So if you look in chapter 25, there's a table that gives the resistivities and the temperature coefficients of resistivities. You want alpha. That's in inverse degrees Celsius. And then you're multiplying that by the change in temperature. So T minus T naught. So you're going to solve this equation for T. And then your uncertainty in T. And so this is a little bit calculated or complicated, but I'll show you the steps. You take your uncertainty in T naught squared. So that's going to be 1 degree Fahrenheit. You're going to convert that to Celsius and square it. Then you want your uncertainty in your resistance that you calculated up here, divided by R naught times alpha. You're squaring that. Then you have R, your measured resistance, multiplied by the uncertainty in R naught. So if you look at the table, what do you know that value to? And that's your, what's the precision of that value? And so that's going to be your delta R naught here. But you're multiplying that by your calculated value of the resistance, dividing by R naught squared times alpha. And then once you get that, you're going to square that. And then the last term, you're taking the ratio R over R naught minus 1, multiplying by delta alpha. So what's your uncertainty in your temperature coefficient of resistivity? So this is your your uncertainty in your multimeter value for the resistance initially. This is your uncertainty in the temperature coefficient of resistance, and so your resistivity, and you're dividing that by alpha squared, and then you're squaring that whole quantity. So you're adding 4 squared terms together and taking the square root. And so that's going to be your uncertainty in temperature. So how precisely do you know the temperature, or so you get an uncertainty in degrees Celsius from that. And if you have any questions, you can just email me. The last thing I want to talk about is the next lab class, which is Tuesday, the 23rd, is the lab midterm. So at 9 o'clock, I'm going to post the midterm exam. It's going to be due 24 hours later. So you're going to submit it as a PDF file onto Blackboard. I think it'll take a JPEGs as well, but I think a PDF file would be better if you can do that. So there are going to be 5 questions, 1 from each experiment, worth 20 points each. So you have 3 types of questions. 1, you can be asked to solve a math problem that's related to the experiment. You can be asked to describe a part of the procedure of the experiment, or you can plot a graph based on similar data to your experiment. So there are 3 different possibilities, and 3 types of questions that you could get. But that's the basic structure of the lab midterm, and that'll be the structure of the lab final as well. So if you have any questions about anything we talked about, whether it's the lab midterm or whether it's the steps for this particular experiment, please let me know via email. Otherwise, good luck with everything, and I will talk to you soon.